Welcome to this video on mathematical induction, a powerful tool in the world of mathematics. We are going to break down the key components of mathematical induction and show you how to use it to prove statements about natural numbers. What's in it for you are: first we will see what is mathematical induction, and then the principle of mathematical induction statement, after which we will see the three essential steps involved in mathematical induction. In that we will delve into the concept of base case, which is the starting point of induction, and next the inductive hypothesis and its role in proof. Next up, the inductive step, which is the core of mathematical induction process. And finally, we will put these steps into action and prove a statement. First, what is mathematical induction? A mathematical induction is a powerful proof technique used to demonstrate the validity of a statement for an infinite set of values. Mathematical induction is a rigorous method used in various branches of mathematics to prove statements for all positive integers, such as properties of sequences, sums, and products. Mathematical induction is a fundamental tool used in various mathematical fields like algebra, number theory, and combinatorics. And it is an instrument in proving a wide range of theorems and propositions. Mathematical induction is a technique of proving a statement, theorem, or formula which is thought to be true for each and every natural number n. We can compare the mathematical induction to falling dominoes. When a domino falls, it knocks down the next domino in succession. The first domino knocks down the second one, and the second one knocks down the third one, and so on. In the end, all of the dominoes will be bowled over. But there are some conditions to be fulfilled. The starting domino must fall to set the knocking process in action. This is the base step. And next, the distance between the dominoes must be equal for any two adjacent dominoes. Otherwise, a certain domino may fall down without bowling over the next. Then the sequence of reactions will stop. By generalizing this in form of a principle which we would use to prove any mathematical statement as principle of mathematical induction. The principle of mathematical induction is widely used in proving various statements such as sum of first n natural numbers is given by the formula n into n plus 1 by 2. To check the validity of such formula, we use mathematical induction. First, we check the validity for the smallest possible value, and then continue for the higher values, and then if it is true for higher, we accept the validity for entire n. The mathematical induction is described in two main forms, the weak form and strong form. These two forms are used to prove the statements about natural numbers. The weak induction is also known as principle of mathematical induction. Strong induction is also known as second principle of mathematical induction. While proving the given statement, we have a procedure. The initial value is considered as base step of mathematical induction, and the remaining procedure is known as inductive step. First, we will see the weak induction, which is also known as principle of mathematical induction. In this, we have three steps. First, base case. Secondly, induction hypothesis. And thirdly, we have inductive step. In base case, we prove that the statement holds for first n natural number, usually 1. This is the initial step in mathematical induction. It is like setting the foundation for the rest of the proof. To do this, you need to show that the statement is true when you substitute the first n natural number, which is 1, into it. That is, we start by checking if the statement is true for the number 1. If it is true, then the base case is satisfied, and you are on the right track. If it is not true for 1, then the proof fails and you can't use mathematical induction. The base case is like the first domino in a chain. If you can successfully show that the statement holds for the first n natural number 1, then you can proceed to the next step. The second step is called induction hypothesis. Here we assume that the statement holds for an arbitrary natural number k. This is like making a temporary assumption as part of your proof. Once you assume the statement is true for k, you use this assumption to prove that the statement is also true for the next natural number k plus 1. And this step is called inductive step. By establishing the connection between the base case and inductive step, you can conclude the statement is true for all natural numbers greater than or equal to base case. Next, strong induction. Strong induction is a way of proving statements about integers where you assume that the statement is true not just for a single number but for all numbers before it. There is up to a certain starting point. In simple terms, you can say if a statement is true for all numbers before, it is also true for the next number. This method allows you to establish the truth of the statement for a wide range of integers, making it a powerful proof technique. We will see the strong induction in detail in next video. Both forms of mathematical inductions are valid proof techniques, and the choice between them depends on the nature of the statement you are trying to prove. Now let's move on and understand the inductive process. And these are the steps for proof by induction. Here our basic step is to validate our statement by proving it true when n equals 1. Then we assume the statement is correct for n equals k. And we want to show that it is also proper for when n equals k plus 1. The idea behind the inductive proof is this. Imagine there is an infinite staircase and you want to know whether or not you can climb and reach every step. If you can reach the first step, that is the base step, we can get to the next step. And if you can ascend to the following step, then you can go to the one after it and so on. So the idea behind the principle of mathematical induction, sometimes referred to as principle of induction or proof by induction, which will show the logical progression of justifiable steps. So base step is where you demonstrate the statement you are trying to prove holds true for the first value of an n equals 1. And it serves as a starting point, providing the foundation for inductive reasoning. And next up we have inductive hypothesis or assumption step. In this step, you make an assumption that the statement holds true for an arbitrary value of n, often denoted as k. This assumption is crucial as it forms the basis for inductive step. And finally, we have induction step. In this step, we use the step 2 to show that the statement is true for n equals k plus 1. And this step essentially links the truth of the statement for k to the truth of the next value in the sequence. Now let's see an example. Here we use the mathematical induction to show that 1 square plus 2 square plus 3 square up to n square equals n into n plus 1 into 2n plus 1 divided by 6. And n is positive integer. First, proof for base case. And in base case, we know that we need to show that the statement or a formula holds for the smallest positive integer, often n equals 1. So consider the given statement as p of n. Now let's solve the left hand side of the statement. In base case, we need to show that p of 1 equals true. In left hand side, we have n square. Substitute n equals 1. So 1 square equals 1. Similarly, for the right hand side, calculate the formula for n equals 1. That is, we are replacing n with value 1. N into n plus 1 into 2n plus 1 divided by 6 is replaced as 1 into 1 plus 1 into 2 into 1 plus 1 divided by 6. On simplifying this, we get 1 into 2 into 3 divided by 6. On numerator and denominator, we have 6, which is equal to 1. Now we have shown that LHS matches the RHS for n equals 1. And the formula holds true for the base case. Note that the base case is not always as 1. Sometimes it could start from 2 or 3 and on and on. In next step, we need to assume the formula is true for k. Here we assume that the formula or statement holds true for an arbitrary positive integer k. This is the inductive hypothesis. We denote it as p of k. That is, we assume p of k is true. Now we have p of k equals 1 square plus 2 square plus 3 square, and the pattern goes on up to k square is equal to k into k plus 1 into 2k plus 1 over 6. Now we need to prove that this next step is true. This is the main crux of the whole process. We need to show that our assumption p of k is true implies p of k plus 1 is also true. To prove p of k plus 1 is true, we need to advance the term in left hand side by k plus 1. Similarly, advance the term by k plus 1 on right hand side also. That is, on both sides we are adding k plus 1 the whole square. On right hand side, you can see the k is replaced with k plus 1. Now we will start by the left hand side of the equation. By inductive hypothesis, 1 square plus 2 square plus 3 square up to k square is equal to k into k plus 1 into 2k plus 1 divided by 6. So by inductive hypothesis, this part will become k into k plus 1 into 2k plus 1 over 6 plus k plus 1 the whole square. In both terms, we have k plus 1. So take k plus 1 common. On taking the common term k plus 1 outside, we have k into 2k plus 1 over 6 plus k plus 1. Now simplify the terms within the square brackets. Now take LCD. To make the common denominator, we multiply the right side by 6. Now do the cross multiply. That is the butterfly method. Multiply the right hand side denominator with left hand side numerator. Again multiply the left hand side denominator with right hand side numerator. Now multiply the denominator of both terms. On doing this, we get k plus 1 into k into 2k plus 1 plus 6 into k plus 1 divided by 6. Now multiply k and 6 with the terms inside the brackets. So we get k plus 1 into 2k square plus k plus 6k plus 6 whole divided by 6. On combining the like terms on the numerator, we get 2k square plus 7k plus 6. Now factor this term. To do this, we can look for two numbers that multiply to the product of the leading coefficient 2 and the constant term 6, which is 2 into 6, 12, and add up to the middle coefficient 7. These two numbers are 3 and 4. Because 4 into 3 equals 12, 4 plus 3, 7. On multiplying two numbers, we should get 12. With the same numbers, while adding, we should get 7. Now the first term coefficient is 2. So divide the terms with 2. On dividing 4 by 2, we get 2. And the second term, we get 3 by 2. On factorizing the equation, we get k plus 2 as the first term. In second term, we have k plus 3 by 2. Now cross multiply. So we have 2k plus 3. Now we have k plus 1 into k plus 2 into 2k plus 3 over 6. We can rewrite the numerator. Write k plus 1 as it is. K plus 2 can be written as k plus 1 plus 1. 2k plus 3 can be written as 2k plus 2 plus 1. We can further simplify this. Write k plus 1 as it is. Factor out 1 from k plus 1 plus 1. In third term, we can take 2 as common. We can factor out 2 and it can be written as 2 into k plus 1 plus 1. We are done now. If you compare this formula to the inductive hypothesis, what you notice is k is advanced by 1. That is, k has gone to the next natural number by advancing the left side of our equation by 1. So this process shows that p of k follows p of k plus 1 and also true. By the mathematical induction, the given statement is true.